Have you ever written a Spark query, hit run, and just been blown away by how fast it is? I mean, it can feel like actual magic. But you know what? It's not. It's something way cooler. It's brilliant, methodical engineering. And in this explainer, we're going to pull back the curtain and see exactly how it works.
So just how fast are we talking about here? Well, our source material shows that Spark can run certain jobs up to 25 times faster than if you just did it the straightforward, naive way. 25 times. That's the difference between grabbing a quick coffee and waiting all afternoon. So the big question is, how on earth does it pull that off?
And that right there is the question we're going to answer today. We're going to follow one simple query on its incredible journey from the moment you type it out all the way to it being executed across a massive cluster of computers. We're going to uncover the secret sauce behind Spark's amazing speed.
Okay, so here's the thing. The secret isn't some single silver bullet. It's actually this really sophisticated multi-stage optimization process. What Spark does is it takes the code you write and behind the scenes it completely rewrites it into a super efficient plan of attack, all before a single byte of your data even gets touched. So the whole journey starts right here. Before Spark can optimize anything at all, it first has to understand what you're even asking it to do. It needs a way to translate your code, which is for humans, into a structured plan that a machine can actually understand and work with. And this is the roadmap for that whole journey. Seriously, every single query you run in Spark goes through these 4 key transformations. So let's just walk through each one, and you'll see exactly where the magic really starts to happen. First up, we have the parse logical plan. Now, at this stage, Spark is not being smart at all. It's not checking if your tables are real or if your column names are right. Nope. It's just looking at the basic grammar of your code, your filters, your joins, your groupings, and it builds this initial kind of messy tree of operations. Just think of it like a very rough pencil sketch. Okay, next, Spark takes that rough sketch and turns it into a proper, validated blueprint. This is what we call the analyzed logical plan. This is where Spark gets out its master list, its catalog, and checks everything. It asks, does this orders table actually exist? Is there really an amount column? Hey, are you trying to join 2 things that can't be joined? If it all checks out, boom, we have a valid plan. It's still not optimized, but hey, at least we know it makes sense. All right, now for the really genius part. Let's talk about Catalyst. This is Spark's query optimizer, and you should think of it like a grandmaster chess player. It looks at our blueprint, that analyzed logical plan, and it applies this whole library of really clever rules and strategies to find the absolute most efficient way to win the game. So, what kind of moves does this grandmaster have? Well, Catalyst has a whole playbook. It does things like pushing filters down to the data source, getting rid of columns you don't even need, simplifying calculations, and picking the smartest way to join data. We're going to focus on that first one, Predicate Pushdown, because honestly, it is a total game changer. Just look at this. This shows you exactly how powerful Predicate Pushdown is. The naive way, on the left, would be to read an entire gigantic table into memory and then try to filter it. That's crazy inefficient. But Catalyst is way smarter. It pushes that filter, that condition, directly to where the data is stored. That way, Spark only has to read the tiny little slice of data it actually needs in the first place. And here's the bottom line, right? Moving data around is expensive. It takes time, it clogs up the network, it eats up memory. So by reading way less data from the very beginning, Spark saves a massive amount of time and resources. I'm telling you, this one optimization can be responsible for a huge chunk of that 25x speedup we talked about. Okay, so Catalyst has worked its magic. We now have an optimized logical plan, but that's still just a blueprint of what needs to get done. Spark still has to figure out exactly how it's going to execute this plan across a whole bunch of different computers in a cluster. And that brings us to the final phase, the physical plan. You know, Spark might even come up with a few different physical plans and then use a cost model to pick the absolute best one. This final plan gets structured as something called a directed acyclic graph, or just DAG for short. And that DAG is the exact step-by-step game plan for getting the job done across the entire cluster. Now, to really get what a DAG is doing, you have to understand one critical concept, the shuffle. A shuffle is what happens anytime Spark needs to move data around and redistribute it across all the different machines in the cluster. Things like grouping data or sorting it, they require a shuffle because all the related pieces of data might be scattered everywhere. Shuffles are super powerful, but they are, without a doubt, the single most expensive operation in Spark.
So the DAG scheduler is smart. It uses those expensive shuffles as boundaries, breaking the entire job up into stages. You see, operations that don't need a shuffle, like just reading and filtering data, they all get bundled into stage 0. Then you hit a shuffle, and stage 1 begins. The key thing to remember is that each stage is a set of tasks that has to finish completely before the next stage can even start. So we followed this query all the way from a simple line of code to this highly optimized multi-stage game plan. But why does any of this matter to you as a developer or a data engineer? Why go through all this?
It matters because this is everything. This whole journey is the secret. That 25x performance gain we kicked things off with, it doesn't come from a faster processor or having more memory. It is created by this incredibly intelligent, fully automated process of planning and optimization that happens every single time you run a query.
And you know what? This quote from our source material just perfectly sums up the entire thing. It hits every key point we just talked about. The multiple stages, the Catalyst optimizer using rules like Predicate Pushdown, and the DAG scheduler breaking the plan into stages right at those shuffle boundaries. It's all right there.
See, when you understand this flow, you can write better, smarter Spark code. You can actually look at an execution plan and diagnose why something is slow. You can structure your jobs to avoid those really expensive shuffles. So the real question I have for you is this. Now that you know the secret behind Spark speed, how are you going to use it to build your next data job?